Welcome to EDU World Space.
Okay, so today we're going to talk about the de Broglie wavelength. So the de Broglie wavelength is the wavelength, associated with all massive particles, and this is related to the principle that all matter, let me write here, that all matter exhibits wave-like behavior. Like behavior. Okay? So to find the wavelength of a matter particle, we use the de Broglie wavelength formula, which is lambda is equal to Planck's constant divided by the momentum of the particle. And we also have an expression on which the momentum of the particle is associated with its energy by E is equal to P squared divided by 2m. Okay? On which this energy is a non-relativistic energy for the particle, of a particle. Okay? Now, in this exercise, suppose that we have an electron and we know that its energy is non-relativistic and is equal to 10 electron volts. So given this, we want to find what is the wavelength of this electron. So we can merge the expression for the de Broglie wavelength with the expression for the non-relativistic energy. So we can write lambda in terms of the Planck's constant, the mass of the electron, and its energy. So let's do this. We have that. First, let me write P is going to be equal to the square root of 2 times the mass of the electron times its energy. Then we substitute P back into the de Broglie wavelength. And we have that the de Broglie wavelength is going to be H times the square root of 1 divided by P. So 2me. Now we just substitute the values. So Planck's constant is a well-known quantity, and I'm going to write it in electron volts because I'm using the energy in electron volts. So the Planck's constant is 4.136 times 10 to the minus 15 electron volts times second times the square root of 1 divided by 2 times the energy, so 10 electron volts, times the mass of the electron. And I'm going to write the mass in terms of electron volts, so 0.51 times 10 to the 6 electron volts divided by the speed of light squared, which is 3 times 10 to the 8 squared. Okay? So just to be clear, this is the expression for the mass of the electron written in electron volts. Okay, and doing this calculation, we're going to find that the wavelength associated with this electron is going to be equal to 3.8 times 10 to the minus 10 meters. Now, question B, we want again to calculate the wavelength of the electron. But this time, we have to suppose that the energy of the electron is going to be 100 electron volt. So for the electron, this energy regime is still non-relativistic, okay, such that we can use this expression. So we are basically do the same thing as we did in question A, but changing the value of the energy. So I'm going to write everything again. So lambda, Planck's constant, 4.136 times 10 to the minus 15 electron volts times second times 1 over the momentum, which is 2 times the energy, which now is 100 electron volts, times the mass of the electron, which is a big expression, 0.51 times 10 to the 6 electron volts divided by the speed of the light squared, which is 3 times 10 to the 8 meters per second. Okay, and doing the calculation, we're going to find that the wavelength is 1.2 times 10 to the minus 10 meters. So you can see that when the electron is more energetic, the wavelength shrinks to a smaller value. Now, in question C, we are going to do the same thing, but again with a different energy for the electron. It's 1 kilo electron volts, which is equivalent to 1,000 electron volts. Still, this energy is in the non-relativistic regime, okay? Because this energy is much smaller than, because it's still much smaller than the rest energy of the electron, okay? Which is equal to the mass times the speed of light squared. Okay, so we are working in the non-relativistic regime, so we are going to use the same expression as we did in question A and B, and the only thing that we're going to change is the energy of the electron. I won't write the whole expression again. Just keep in mind that instead of 100, I'm going to be using 1,000 electron volts. And by doing this, we're going to find that the wavelength will be 3.8 times 10 to the minus 11 meters. Again, we are seeing that as we increase the energy of the electron, its wavelength will be reduced. And with this